Swayam Prabha. Digital India. Educated India.
Good morning, everyone. So today, let's get started with the second session of supervised learning. We'll start with a brief summary of what we did last lecture, and then we'll see how to proceed from there. So if you remember, last lecture we started with doing linear regression, right? So where the label space was the set of all real numbers, and the model that we try to fit to the data was a linear model. So in particular, we looked at this kind of an objective function, y squared, and then we try to minimize it over w. So this was the objective function that we tried to fit in yesterday's class. And what we also did was we tried to we derived an analytical closed form solution for the actual w that minimizes the objective function. We try to understand that what the geometric interpretation of we understood the geometric interpretation of what the w. In particular, we saw that the w that we get out of minimizing this least squares objective is just the projection of the target or the label vector onto the space of subspace spanned by the feature vectors. So we also try to link the solution that we got to a maximum likelihood formulation. So where we said, where we tried to show that if your y was w transpose x plus epsilon, where epsilon is some Gaussian noise with mean 0 and let's say variance 1, then if you did a maximum likelihood estimate for your data, then for your w, then that estimate is exactly same as minimizing the least squares objective, right? So this is where we ended yesterday. And what we also finally said was, so we wanted to get an iterative method for linear regression. In particular, this was the closed form expression for w, if you remember. And the problem with this was that, so it involves this pseudo inverse of a huge, potentially huge matrix. And when the number of points or dimension is like huge, then doing this inversion is going to take a lot of time. In particular, if it takes like at least n to the 2.6 or n to the 3. So we wanted an iterative method to solve the least squares problem. And the reason why we wanted that was the way we were trying to think of it was we start with some w, and as you go along the iterations, you wanted to improve this w so that eventually you get to a w which minimizes the problem that we wanted to solve, right? So that is where we stopped. And I hope in the lab session it was also covered how the modeling actually affects when the true model is not really what you are trying to fit, or if when the number of data points increases, how you will be able to overfit and underfit, and those kind of things were covered in the lab session, I hope. So today I would want to go back and do something very basic. So we want to understand how to get to this iterative method for solving this problem, right? So for this, we need to do something in optimization. So today's class, we would cover a bit of basics of optimization. So I want to do a quick basic optimization detour today. So give a flavor for what an optimization problem is and why it is important and why it appears all over the place in machine learning, right? So so if the three pillars of machine learning, so to say, are linear algebra, probability, and optimization. And why are these three important? Because all the data that you have in real world has some structure to it. And the best way to understand this structure is through linear algebra. And whenever somebody gives you data, it's never noise-free. So the noise will always be there in the data because of human errors or because of measurement errors and so on. And the scientific way to deal with noise is using probability. And machine learning is all about making decisions, right? So you want to minimize a cost function, you want to maximize your profit and things like that. So and the way to deal with decisions is through optimization. And today we will look at this third pillar of machine learning, so to say, which is optimization. And then I'll try to relate it to how that can be used for the linear regression problem that we tried to see yesterday. So why is optimization important? So here is a picture. Anyone knows who this person is? Okay. So this is a famous mathematician Euler, so who said, since the fabric of universe is most perfect and work of a most wise creator, nothing at all takes place in the universe in which some rule of maximum or minimum does not appear. So, so this kind of gives an importance of why optimization of and objective functions and optimization is so inherent to the problems that we try to solve. So to give you some simple example, right? So let's say you are here and you throw a ball up, and what you want to find out is you want to plot the height of this ball with respect to time, right? So now you start with the ball starts at this point and it ends at the next red dot. So how would this plot look like? Any question, any answers? Sorry? So, for example, can this plot look like this? So what kind of a function would this be? So would this be a parabolic function? For example, can this be the path traced by the ball with respect to time? Yes or no? How many of you think this possibly is a way? I mean, I'm throwing a ball to you, right? So would it travel this way? No. So, so what shape would it take? It is a convex function, somebody says, but even simpler, right? So it would just be a parabola, basically. And of these three, which do you think is a more reasonable parabola? This one, or the red one, or the green one? Well, why is it the red one? So I didn't give you any numbers. So anyway, so you can of course use your Newton's laws and figure out this is a parabola and exactly plot the parabola. But there is a interesting way to look at it as well, and that was proposed by this person. And what he says is, so you can define something called as action at a point, right? So at a point, by my meaning a point that in the path traced by this ball, and you can define it as the difference between the kinetic energy and the potential energy of the ball, right? And the action for a path traced by this ball is just you integrate it over the path in which the ball travels, right? So now, interestingly, nature optimizes and figures out the path of least action, right? So this is how this is an example to say that nature inherently does some optimization. We don't know why, but that is how it is, right? So if you define your action as in this particular form, then nature chooses the path of least action. So this is just to show that optimization is inherent to the problems that that we see all around us, right from physics. And there are more examples. So for example, if you look at the path traveled by light from one point to other, it travels in the path of the least time, right? So, and similarly, there are examples in thermodynamics, and so this is another Occam's razor, which is kind of saying that among competing hypotheses, if you want to explain something and then you have like 10 different ways to explain the same thing, the hypothesis with the fewest assumptions should be selected. And this is often used in machine learning as well. So to find out what best explains data, let's say. Right? So this is just to give an example. These are examples to give why optimization is important, but then let's actually get to the main problem that we are trying to solve. So we'll again start with an example. So let's say I give you a problem where, and these are the points in the problem. So a hungry cow is at position 2, 2 in an open field. Let's say it's an two-dimensional open field, and then the cow is at this particular position, right? And now it is tied to a rope that is 1 unit long. And there is grass at position 4, 3, right? and there is a perpendicular electric fence that passes through the point 2.5 comma 2. So to visualize this, let's say this is the two-dimensional field that we are looking at, and this is where the cow is, right? So it is at position 2 comma 2, and it is tied to a rope that is 1 unit long, which means what does this circle indicate? Yeah. So this is where this is the area in which the cow can actually move around, right? So because it's tied to a rope that is 1 unit long, and and there is some grass at position 4 comma 3, and an electric fence passes through the point 2.5 comma 2. This is like a perpendicular electric fence that passes through this point. Now the question is, how close can the cow get to the fodder? What would be your answer to this problem? Or rather, how would you try to solve this problem? What is your thought process? So what are we trying to solve here? So what is our objective, so to say? Minimize the distance between the grass and the cow.
The constraint is it should be below the.
How many constraints are there? So what are these constraints?
Inside the circle and it should be below the fence.
It should be onto the left of the fence, right? So let's make this more formal. So what do we want to find? We want to, so this is the position of the cow. Let x comma y be the solution, which means the answer to this problem. And so what do we want the solution, the answer, the point, the closest point of the cow to the fodder to actually satisfy, right? So we want to satisfy this particular objective function, right? So why is this the right objective function? So x minus 4 squared plus y minus 3 squared. So what is this function? So what is this capturing? Sorry? So this is, so this is this precisely, right? So this is just the distance of x comma y to the grass, right? And as we said, so we are asking for how close the cow can get to the grass, right? So which means we want to minimize the distance of the cow to the grass, and we are saying that the cow is at position xy in the final answer that we have. So we want to find out the, okay, distance squared, somebody said. So we want to find out, we want to minimize the distance between the cow and the grass, right? So that's why this is the objective that we care about. And what restrictions that the cow has? Somebody said there are 2 restrictions, and let's formalize that also in mathematical way. So the first restriction would be, there's a rope constraint, right? So what is the rope constraint? The rope constraint says the cow has to be within the circle of radius 1, and which means, so if you start from 2 comma 2, which is where the cow is, and it cannot move beyond the circle of radius 1, which means any solution x comma y that you finally say as the answer should necessarily satisfy the condition that x minus 2 squared plus y minus 2 squared is less than or equal to 1, right? So is that clear? Because it has to be within that circle. So it better satisfy this constraint. So the next constraint is the fence constraint, which says that the cow has to be necessarily to the left of the perpendicular line. And now that can be formalized as saying that the x coordinate of the cow has to be less than or equal to 2.5. I don't care about the y coordinate. The fence constraint, if you did not have the rope constraint, the fence constraint just constrains the x coordinate of the cow. You don't really care about the y coordinate, right? So is there anything else that that we need to think about for this problem? So is this clear? So why we are setting this up like this, right? So this is the formal way to set up this problem, and now you can minimize this. Now the question is, how do you solve this problem, right? So what is the answer to this problem? So that is what we'll try to do now. So the framework that we are trying to consider here is an optimization framework to make it more formal. So you have these variables x comma y. In this case, the position of the cow. This is a variable because this is what you are trying to optimize on, right? So this is what you are trying to find out as your answer. And Your objective is the distance from the grass, which can be formalized as x minus 4 squared plus y minus 3 squared. And your constraints are these two. There's a rope constraint and there's a fence constraint, right? Yeah, so the general framework of optimization problems is maximize or minimize some objective, which is just a function of your variables that you're trying to solve, subject to some constraints, which are also functions of your variables, right? So this is the general framework, and now we'll try to see how we can solve this problem. Right, so let's first look at the unconstrained case. I know in the first part of this lecture series, Sridhar covered a bit of unconstrained optimization problems, but then I thought it would be better to do it in slightly more detail so that it can be linked back to the machine learning problems that we are looking at today. Anyway, so that's the goal here. So let's look at the unconstrained case. So in the unconstrained case, let's say there is no fence constraint or rope constraint, right? So if this was your constraint, what would be the solution to this problem? 4, 3, and why is that? Why should it be the minimum?
Because the distance is always positive.
Distance is always positive because you are just summing up two square terms which are positive, so it has to be this, right? So the curve starts at 2, 2. So now here is a way to solve this problem, right? So this is an easy problem. I mean, because you're saying we can look at it and solve the problem. But then let's say we are trying to solve it in a different way, where let's say the curve starts at a particular point, 2, 2, right? And then you compute the objective at this particular point, right? And then the objective happens to be what? In this case, 2 minus 4 squared plus 2 minus 3 squared, which is just 2 squared plus 1, which is 5, right? So now we don't know if this is the right answer to this problem, right? So what we can do is we can try to find out a different. So let's say I try to look at a different point. So in this case, it is 1, 4, and in this point, the objective happens to be 1 minus 4 squared plus 4 minus 3 squared, which is 10, right? So your goal is to minimize the objective, and you are not improving here, right? So it's a bad idea. This is a worse point than the point you started off with earlier. You can try a different point. In this case, I think it is 4, 2, and then the objective happens to be 1, which is smaller, and so on, right? So what is the problem with this idea is because we are not searching for the points that we care about in a principled way. We are arbitrarily searching, and that's not a good idea, right? So you need to do your search in a principled manner, and the question is, how can you do it in a principled manner? Right, so what we have is, so every time I look at a point, I know the objective function at that point, in the sense that I know the distance of the curve of that point to the grass. So that is what is given to me, right? So, and I need to use that information to make a principled guess for the next point in which I need to look for the answer, right? So what basically we need is the curve at a given point, if it knows everything about the information at this point, it needs a good direction in which it has to move, so that in the new point that it ends up in, it is much better than the current point that it starts off with. So this is the goal. So the whole goal of optimization now becomes to search for this good direction to move from the current point. Now we will want to see how can you figure out a good direction, right? So this is the key question of optimization. What is a good direction, right? So, and the whole of today we'll try to formalize this basically. So let's take a simpler problem. Forget the curve for a moment. So the problem that we care about is y equals x squared plus 2, right? So, and if you want to minimize this, what is the solution to this problem? So where does this curve attain its minimum? X equal to 0, and what is the objective value at that point? 2. So that is the solution to this problem. I mean, of course, we are looking at easier problems, but then when you go to complex problems, you cannot like really look at it and say the answer. So that's why we care about all this direction finding and so on, right? So let's say we start at point 8, right? So now, how many directions can you move in this space, in the real line space? From this point, how many directions are there? So why infinite? Why are there infinite directions? So I am at this point, so I have a choice to go in how many directions to search for the next point? Sorry? 2. And what are these directions? so in this case, it's just you either move to the left or you move to the right, right? So if it is 0.8, which direction would you want to move to? Would you want to move to the left or would you want to move to the right? You would want to move to the left because why is left a good direction? It is closer to the optimum in the sense that you expect the objective function to go down if you move to the left, right? Whereas if I am in 0.5, then, minus 0.5, then the direction that I would want to move is to the right, right? So now, as a function, right, so now we want to somehow relate this direction to the function that we are trying to optimize. Right? So the function that we are trying to optimize is x squared plus 2. Now given any function and any point, we want to find a direction which will take us to a better point, right? So now how can you relate this direction to the function? So any thoughts on that? Direction of the tangent at that point. So which basically is the derivative at that point is what you're saying, right? So in some sense, basically in general, all you need in this particular case is if x is greater than 0, then you want to move to the left. If x is less than 0, then you want to move to the right, so that your objective becomes better and better. So somebody says tangent. So so even coming to that, so let's say if you had such a direction, right? So what you could do, you can start with your current value for x and then move in that direction, and then the next point your new x would be the step that you've taken in the direction that you have chosen, right? So in particular, if current x is greater than 0, we want d is less than 0. So the addition value that you are adding to x should be less than 0. If current x is less than 0, we want d to be greater than 0. Right? So in this case, d is just a number which also indicates a direction. If your x was like a higher dimensional space, then it would just not be a number, but then it would also be a vector. Right? So we will come to that in a minute. But the directionality is indicated by the sign in this case because it's just a one-dimensional thing. Right? So how can you choose d? So somebody said derivative. So let's look at the derivative of this. Right? So what is the derivative of y equal to x squared plus 2? Right? So if let's say f of x is x squared plus 2, f dash of x, as you all know, is 2x. Right? So now is this giving us the answer? Is the question, right? So this is what we wanted to satisfy. Is this satisfying this? Which means, so in this particular case, right, so if your x is greater than 0, is your derivative less than 0? And if x is less than 0, is your derivative greater than 0? Is this satisfying this or not? So you get what I'm asking? So if this is the value that you're going to add at a given x, right, to find your new x, so is 2x satisfying this constraint? So what is the derivative of current x, which is 2 of x? So as you see, your derivative does not give you the answer that you want, right? So your 2x for anything x greater than 0 is actually positive, but then if your x is negative, then your 2x is also negative, right? So what actually does the trick in this case is the negative of the derivative, right? So which is minus 2x in this case, which has the property that if x is greater than 0, your d is less than 0, and if x is less than 0, your d is greater than 0, right? So for example, if your x is 0.5, then the negative of the derivative at that 0.5 is minus 1, right? So let's say, so now our algorithm was what? So you start with some x, let's say it was 0.5, and you compute the derivative at that point, take its negative, and then move in the direction of the negative derivative, right? So which means your new x would be current x plus d, which in this case is minus 1. So you start with 0.5, and where do you land now in this case? So you end up at minus 0.5, right? So now your new x would be minus 0.5. So now what you do, you again do the same thing. So what you start with your new x, and you compute the derivative at your new x, and then take a step in the direction of the derivative. What is the derivative at your new x, which is minus 0.5? Yeah, so we started with 0.5, and then we ended up at minus 0.5. Now if you start with minus 0.5, where do you go? So what is the derivative at minus 0.5? It's just, is it 1? What is the derivative? What is the derivative at minus 0.5 of y equal to x squared plus 2? Minus 1. So we said we'll travel in the direction of the negative derivative, right? Which means you have to add a minus of minus 1, which is 1 to this. And where do you end up if you do that? You end up here. Now what you do? So you again compute the negative derivative at 0.5. So what happens? What is the problem? So you started with 0.5. So if you traveled in the direction of negative derivative, you ended up minus 0.5. You again start at minus 0.5 and travel in the direction of negative derivative. You end up at 0.5. You keep doing this, right? So the problem is what? The problem is you are kind of toggling between minus 0.5 and 0.5. So how can we solve this problem? What can you do with the second derivative? So in this case, the second derivative is what? It's just 2, let's say. How would that help? Probably not, right? We are trying to find the minimum of this curve. So true. So yeah, so we are looking, so in this particular problem, that's an easy way to solve it, right? So, but there are problems where your derivative, setting a derivative to 0 and solving it might not be an easy solution. You cannot really do that. So that is where I'll get to eventually. So here, the understanding, yeah, that is the thing. So the understanding is we start at a point and then we take a step in the negative direction of the derivative, go to a next point and then keep doing this. The problem we are hitting it is it's kind of oscillating between 0.5 and negative 0.5, right? So what did we do when we went from 0.5 to negative 0.5? What happened there? What was the problem? So ideally, you should have stopped at 0, but then you went till minus 0.5. You are making a big jump, right? So your jump that you made was large, right? So which means you jumped so much that you missed the negative, missed the minimum. And again, you are making a big jump, right? So now how can we make sure that this jump does not happen too much? So how can you solve that problem of this big jump? Sorry? So Newton's method is a different thing, but then in this particular problem that I give you, right? So from 0.5, you know that you want to reduce the size of the jump. That's all, right? So you start at a point, and then you decided a direction which is given by the negative derivative. But then the problem is that direction might give you a large jump, right? So you now want to make a smaller jump, which means you only take a smaller step in that direction, and that's all you want to do, right? So the way to control this problem is to look at step size, basically, right? So now how can you modify the step size at every point to avoid this problem? So if you make a very small, if you take a really small step size, then what is the issue? Let's say from 0.5, I'm taking a step size of like 0.00001. You will take a very long time to reach, or you might never reach it, right? So you can run the iteration for infinitely, but then you might never be able to reach the solution. So if you take a large step size, the problem is you might miss the minimum. So now how can you kind of balance these two? Mm-hmm. Correct. So, but you don't. Mm-hmm. It will control the jumps. So we need to somehow fix how much we are jumping. The algorithm is in our control, right? So we can make any jump that we want to, but then the goal is eventually you need to get to the minimum. So if you make very small jump at each iteration, then you might never get to the minimum. If you're making large jumps, again, you might toggle and so on. So one way to solve this problem is to keep reducing the size of your jumps over iterations, right? So you start with maybe a large jump, but then over time, the jumps that you make should be smaller and smaller. So which means as you get closer and closer, so you're making smaller and smaller jumps so that eventually you will get to the minimum. So there is a formal way to state that, saying that if your jumps are of a particular type, then you will this method will eventually go to the minimum. But I'm not going to formally state or prove that now.